lifetime, and safety. My name is Chris Niva, Marketing Operations Coordinator here at Thermal Analytics and host of today's webinar. Our presenter today is Zach Edel. Zach is a senior research engineer who has been with Thermal Analytics for over 5 years. Zach is TAI's resident battery expert and chief engineer of the TAITherm battery extension. He is involved in thermal electric and thermal CFD simulation, advanced physics modeling, algorithm development, and multi-physics coupling. He has over 13 years of research experience developing advanced physics models, performing numerical modeling, and performing experimentation and data analysis. In 2013, he received his PhD in mechanical engineering mechanics from Michigan Technological University. Throughout this presentation, you may submit questions in the question box, and we will review them at the end. We're also recording this webinar, and we'll be sending you the link following this presentation. And with that, Zach, if you are ready, you may begin.
Okay, thanks, Chris. So today I'll be talking about battery modeling with TAITherm for performance, lifetime, and safety. First, I'll go through an introduction and a little bit of motivation on why we do battery modeling. I'll talk a little bit about the battery models that are currently available in TAITherm. And then I'll go through a few case studies where we have examples of results that we've gotten in the past and a few different things that you can do with our software. That'll include a hybrid electric vehicle, a battery electric vehicle, and thermal runaway. And then I'll talk about some of our new features, both in the current release and what we have planned for the future. Some of the current challenges in electric vehicle batteries mainly is thermal management from the vehicle side. That means keeping the batteries cool enough to maintain the lifetime of the batteries and make sure that they don't go into thermal runaway and create a safety hazard. You have to consider the lifespan. Even though batteries operate performance-wise better at higher temperatures, it quickly degrades the batteries and creates a major warranty issue when you're talking about a battery pack failing before the full life of the vehicle is reached. You need to make sure that the battery pack is going to perform in harsh environments. Make sure it has enough capacity so that the customer is satisfied with the driving range. You need to consider charging time, safety, like avoiding thermal runaway or making it safe to exit the vehicle if a thermal runaway event occurs. And also looking at cost. The electric vehicles need to be able to compete with gasoline vehicles, and that's very difficult, especially with the price of lithium-ion batteries. But that's quickly going down, and people are finding new ways to meet those requirements. But minimizing the cost of your design is critical in all aspects of engineering. The battery models in TAITherm are thermoelectric models where the electrical and thermal behaviors are coupled. So the battery resistance depends on temperature and depth of discharge, and the temperature depends on resistive heating and the chemical reactions that occur. So the battery models compute an imposed heat that's applied to the battery geometry, and that imposed heat is computed by solving electrical circuit equations as functions of temperature and depth of discharge. We have 3 different models that are available. The simplest one and easiest to derive is the NTG equivalent circuit model. It's very common. It's also fairly simple. It's just a voltage potential and an internal resistance in series inside the cell. Just a simple electrical equation. Then we have the NTG distributed model, which takes this model and applies it on an element level across the faces of the electrodes, which are modeled explicitly in the software. And that gives you a voltage gradient across the faces of the electrodes. You get local current density, local depth of discharge, and that allows you to look at how the active material is being utilized and localized heating and things like that. So that's really more of an internal cell model. And then we also have the NREL equivalent circuit model, which is similar to the NTG model, but it has some additional filter circuits in it, which are RC pairs on the electrical side. And what that does is it adds a time constant to the battery behavior, actually several time constants to the battery behavior to capture transient effects and more accurately model drive cycles when current and voltage are changing at a high rate. So now I'll talk about a few case studies that we've done, and these are mainly cooling, insulation, and heat protection. So some of the battery design considerations that people commonly look at with modeling software depend on different levels of modeling. So you have a cell level where you're looking at individual cells, both internal and external, mainly looking at uniform current distribution through the pack, temperature distribution, and internally you can also look at the uniformity of utilizing the active material. You can look at hot spots in cells and see what your internal temperatures are and make sure they're not exceeding safe limits, and that the lifetime is going to be substantial enough to satisfy customer needs. And then at a pack level, you want to look at uniform cooling and make sure that the temperature is similar across the pack so that different cells aren't receiving different temperatures and so forth based on being upstream or downstream in your cooling system or being closer to an external environment or something like that. And then at a system level, you can also look at cell balance like battery management systems and overall state of charge estimation. You can look at extending the capacity and the lifetime of batteries with different control scenarios and how capacity is going to depend on environmental temperature and also different driving considerations such as drive cycles and cabin cooling strategies and things like that, so that you can make sure even when you have these other systems present in the vehicle, your battery pack is going to give you the desired range and durability. And also we're working on integrating these battery pack capabilities with other components in the vehicle. You can look at different cooling strategies. There's air cooling, liquid cooling. There are heat sinks, cooling plates, heat pipes, different things like that. And new technologies are being created every day, and modeling is something that helps us to evaluate how important those technologies are or how reasonable, and whether or not that's something that you want to implement in your vehicle. And then for hybrid and electric vehicle batteries, the main aspects that people typically look at, and generally you have to look at each one of them to make sure that your battery is going to perform. First one is performance, just to make sure that you're getting the right power output from your battery, both at the beginning of life and at the end of life, that you have capacity, that you can operate within temperature limits without derating the battery, and operating at a lower power output to maintain battery health. Then you also have lifetime and durability, where we're looking at how long the batteries are going to last, and possibly how we might modify how those batteries are used in the vehicle to extend the lifetime of those batteries. Sometimes plan for secondary use applications where you can sell your batteries to a stationary storage facility or something like that. And also looking at what the minimum remaining capacity is that you can run your battery down to before replacement occurs. And then the last one is safety, which is mainly looking at thermal runaway, and that's when a fault event happens and the battery goes into thermal runaway, which is an exothermic chemical reaction where basically it burns up. We want to make sure that we can either mitigate that to the point where the entire pack doesn't go up in flames, or at least give the occupants of a vehicle time to escape the vehicle in time a warning and then time to escape the vehicle before a catastrophic event occurs. So our first case study is the plug-in hybrid vehicle. So we have a 4-volt nominal cell. This is a prismatic cell, so the electrodes are wound in a jelly roll and then kind of smushed down and stuck in a can. And this is common in a lot of hybrid electric vehicles. It depends on what manufacturer you're going to, but it's a high capacity, compact means of storing energy. And we're going to connect these 12 cells in series to have a 48 volt pack voltage, and then connect those modules with parallel connections to increase the capacity of the pack. So the modules are organized into a pack, and the pack is located in the vehicle underbody of this hybrid electric vehicle with an exhaust pipe running through it. And then we're looking at different packaging materials, conduction pathways, heat shielding materials or numbers of heat shields, things like that in this scenario. So several different design strategies were considered. We're not presenting all the results here, but basically we're looking at different heat shielding materials and things like that to make sure that the batteries are going to be protected and cooled substantially. So these are some of the results from the software. For the first 10 minutes, the batteries are driving the vehicle, and so they're heating up from discharge. And then after 10 minutes, the vehicle turns on, the exhaust pipe heats up, and the batteries go into a charge mode, which is actually a lower current in this case. And in that case, the batteries are still heating somewhat from discharge, but the main consideration in that case is then shielding the batteries from this hot exhaust pipe. So it's important to recognize heat sources both inside and outside the pack. While the vehicle is being driven in electrical mode, you need to dissipate all of the heat inside the pack, or enough to maintain the lifetime of the batteries. And then whenever the vehicle's driving in combustion engine mode, you have to shield that pack from external components getting too hot. So there are different considerations here, and they're actually design trade-offs where adding more protection might insulate the pack more and cause a higher temperature inside the pack, but then you can maintain your cooling strategy to limit the temperature of the cells. So this kind of simulation allows you to look at a lot of different design alternatives, and in a short amount of time with minimal effort, so that you're not prototyping and going through expensive tests. And it also allows you to do principal component analysis, where you're looking at what are the main design considerations that are driving the constraints that you have to put on this system, and look at what your strategy should be and how you might be able to change what your heat protection and packaging strategy is based on simply knowing what the primary modes of heat transfer are, what the sources are, and what the relative magnitudes of those things are. The next case study I'm going to go through is the Tesla type battery pack. So we've taken a piece of a Tesla module here with 18650 cells and connected them with 3 different cooling strategies. So the boundary conditions are that the ambient temperature in the cabin is either the ambient temperature of the outside or it's 20 degrees Celsius. And that's important when we have the air cooling scenario, because the air is coming from the inside of the cabin. This is located in a vehicle in Yuma, Arizona. So that's in the desert in the United States. It gets very hot. You have a lot of radiation from the ground and the sun. And so we've got a weather file producing weather effects in this case. And we have a background which is outdoor and asphalt. So the pack receives a lot of radiation from the hot asphalt underneath the car. and also incident solar radiation from the sun. It also has radiation heat exchange with the environment, like the sky and so forth. So this is a fully natural weather environment that's being considered. And that really helps to nail down the boundary conditions on the pack itself, since there are a lot of assumptions that have to be made of what the external pack temperatures are, or what the heat transfer rates and incident solar might be. So having a natural weather environment available in TAITherm is a way to get more accurate boundary conditions and make less assumptions, which might jeopardize the accuracy of the model. So the three cooling scenarios that we're considering are passively cooled, air-cooled, and liquid-cooled. In the passively cooled case, we have one air node inside the pack, and it's just exchanging heat through natural convection with both the cells and the external surfaces of that module. For the air-cooled case, we have coolant coming from the cabin. So while the vehicle's running, we're maintaining that at 20 degrees Celsius using the HVAC system. While the vehicle's not running, it's actually turned off. So coolant operating time is drive mode only. And the fluid model is 6 air nodes that are going down the length of that pack. And that's exchanging heat with the cells, and that air is actually heating up, and each node has a volume and a certain number of cells that it's connected to. And then as it exchanges heat with those cells, the air temperature is increasing, and we can look at temperature distribution and things like that inside the pack, make sure we have uniform cooling. And then the liquid cooled case has a ribbon cooler, similar to the Tesla design, where we've got this extruded kind of flat ribbon that runs in a serpentine pattern through the pack. And that has fluid streams in it. So we've generated a number of fluid streams that run through the length of this serpentine channel. And then the cooling at the inlet is 10 degrees Celsius. It's also operating in drive mode only. And we can also see how that coolant heats up and how flow rates affect the temperature and so forth. The drive cycle that we're doing here is actually something I think that was measured on a dyno. It's highly transient. It has several driving periods throughout the day. It's kind of like stop and go driving. So it includes regenerative braking. It includes high acceleration, and this might be something like a service vehicle that's doing deliveries or something like that. But basically, we're running this model on a 1-second time step, and while the vehicle's running, and then while the vehicle's not running, it might be like a 30-second time step to capture the thermal effects, but without all the transient electrical. And this model takes about 6 minutes to run, I think, with this highly transient drive cycle, and this is over a 24-hour period. So it's a very quick approach that allows you to run lifetime models over many years with changing boundary conditions and get accurate lifetime predictions. The average cell temperatures are reported here over a given day in 4 different months out of the year. And the ambient temperature is shown in the dotted line. So we've got an ambient temperature that's changing throughout the day. And then we have average cell temperatures with the solid lines for the 3 different cooling cases. So there are some interesting effects here for the case that's not cooled or passively cooled with no forced convection. The cells are heating up significantly while the vehicle's running, and slowly cooling off while the vehicle's not running. For the air-cooled case, it actually depends on flow rates and things like that, but in this case, I think the cells are still heating up in most cases while the vehicle's running. Depending on the time of year and whether or not the ambient temperature is higher or lower than the coolant temperature, those cells can either be heating up or cooling down while the vehicle's running. And then for the liquid-cooled case, what we actually see is that the liquid cooled is cooling the cells while the vehicle is running, and then the cells are heating up during warm months while the vehicle's not running. So in that case, it's a very efficient cooling system. And the main consideration when you're looking at something like pack lifetime is actually what's happening when the vehicle is not being driven and is sitting in a hot soak scenario outside where the sun is beating down on it and you have high ambient temperatures and so forth. And also what happens during fast charging when the coolant system may or may not be running. And we have a lifetime model that is available with our co-simulation software, TAITherm. And this was developed by the National Renewable Energy Laboratory. It is an empirically based model that has acceleration factors built into it based on state of charge, depth of discharge cycling, and temperature. It is physically justifiable. It looks at both calendar and cycling fade and combines the two to get an accurate lifetime prediction. And with that, you can see different effects for the different cooling scenarios here. First of all, you can see it's a wavy profile because we're running this using the co-simulation driver to import different boundary conditions throughout the year and actually get a degradation that's based on the ambient temperatures at that time of year. So we see higher degradation in the summer, lower degradation in the winter, and that fluctuates throughout the lifetime of the battery, so that we're not using like just an average temperature profile that we just kind of assume for the whole year, which you don't really know how accurate it is when you do that. So it requires multiple simulations to get an accurate aging prediction, and that's what we've done here. You can see the not cooled case is about 10 years. So this is not a worst case scenario. This would be a passing pack for the not cooled case. But end of life is generally considered 70 to 80%. And you can see here that the air cooling extends life by about 2.5 years, while liquid cooling extends life by over 5 years. And you can also see the resistance increase, which is important when we're talking about the amount of power that's available. You can see here the resistance just about doubles over the lifetime of this pack. So when you're talking about the power output, higher resistance is going to mean lower power. It's also going to mean more heat generation. So there's some important things to consider with that as well. And then we can look at the results of geographic location. Hotter environments have higher degradation. And then we can look at thermal runaway. So this is the propagation of thermal runaway is an exothermic reaction that happens in each cell when the reactants start to burn and decompose. It propagates from cell to cell. This can ruin an entire pack, and you also get these flames that are escaping from the cells, which impinge upon neighboring cells and cause them to heat up and go into thermal runaway themselves. So there's a regulation in Europe and Asia called GTR20, which creates the limitation for thermal runaway in a vehicle to be 5 minutes after the user is warned about it. So thermal runaway is a very energetic event. When something goes into thermal runaway with the amount of energy density that's packed into these energy management systems, it's hard to keep it from happening ever. And when it does happen, it's probably going to propagate throughout the pack. So what the restraint is right now is just that it is mitigated enough to happen slow enough to give passengers a safe amount of time to exit the vehicle, so that if catastrophic failure does occur, it's not going to endanger lives. So we have an NREL thermal runaway model available in TAITherm. This is something that is implemented as a script right now, but we are looking at compiling this into the actual software. And this is an example here of thermal runaway with these different packs here. This might be something like you see in an astronaut spacesuit or something like that with 18650 cells. I think this might be a model from NASA. But we're separating those cells using these containment units, and we're looking at different wall insulation thicknesses and so forth. And we can see by isolating these cells, we're slowing down the thermal runaway process to the point where the worst case here, which might not be an absolute worst case, but it takes about 5 minutes for the entire pack to go into thermal runaway. As we add insulation, we extend that out to 29 minutes. So this would be considered a success, I think, if we could do this. There was also some external cooling involved in the third case. And then we've got some new features. We created a new battery interface that allows you to set up battery packs inside the GUI. So this used to be done in an external configuration file that was a text document. Now it's a fully integrated setup utility inside the software. It reduces data management. There's less opportunity for model setup errors, reduces model setup time, and it's a user interface that's very familiar for TAITherm users and is consistent with all of our other widgets and tools in TAITherm with all the same features that are available. So this is a picture of it. We've got our models specified here, cutoff voltages, electrical sources, got all the cells spelled out here. All these boxes are like drop-down boxes with check marks or selections. You can do multi-row selection. And basically it's modeled after the summary table with a few additional capabilities. So it's something that people generally already know how to use. It's quick to use, intuitive, and much easier than dealing with a text document. And then we also have an import-export function that is similar to the boundary condition table that allows you to actually set up an entire pack using Excel and then save that file as a CSV and import it directly into TAITherm, and it will create cells for you, create buses. You can also just use this to modify your setup using automation. So if you want to run this from a command line or something and update some of these parameters, you can tell it to update depth of discharge or scale resistance, and it will automatically make those model changes from a command line interface. So that allows you to couple with other softwares and allows a lot of flexibility in how you want to set up and use that model. We have a new model parameter generator that's it's actually based on MATLAB code, but it has its own GUI. It goes through piece by piece and allows you to fit parameters in an interactive format. And the end of this process is that it generates the battery configuration file coefficients that TAITherm uses. So basically, you just go through this tool, hit generate config file, and you're done with your setup. Future work, we're going to integrate the coefficients that are generated from that text file. So the electrical setup used to be completely in a text file. We've taken everything except the coefficients and put those into the GUI. But the coefficients are still remaining in a text file. So it's somewhat easy to use because we have a tool that generates them, but we'd like to integrate those into the application itself in the future. Integrated post-processing, so we'll add some features so that you can look at electrical parameters in the GUI. And then integrating with different EV components. So we have power electronics, entertainment units, cooling loops. So we're looking at motors, inverters, chillers, heat exchangers, things like that. And some of that is possible in TAITherm if you're good at using it and doing some custom scripting. But what we're looking at doing is creating something that's a lot more powerful for a user to do in a timely fashion and without a whole lot of training. So we'll provide some library components and standard set of procedures to model these different components and then interface them with the battery. And that's all we have for presentation, so I think we can take some questions.
Yes, okay, so first question, can TAITherm co-simulate with AIM-Sim?
I believe so. TAITherm has a very robust way of interfacing with TAITherm and as well as other softwares. So we do have some software interfaces built into TAITherm with their API specifically to exchange data in a rapid fashion. But you can also interface with these other softwares using text files and automated import-export features. So there are different tools that allow you to do that. And we do couple with TAITherm with the battery extension with other softwares such as MATLAB or CFD, or we're working on an FMU, FMI interface right now. So I don't think we've run into a roadblock so far that we can't overcome. And we're building more automation into that process all the time.
Okay. Is your tool capable of simulating electrochemical reactions?
At this time, we don't have an electrochemical model. We're actually working with a partner right now that sells a compiled electrochemical model that we're looking at implementing in TAITherm, at first using coupling and possibly eventually completely integrated. But I would say right now it's in the research and development phase, and it's something that we're looking at getting done in the next couple of years, probably.
Okay. Next question. How are the cells in the batteries discretized in each of the NTG and NREL models? Is a cell size and number one of the inputs?
It's an empirical electrical model. So you derive coefficients based on test data that gives you cell electrical and heat generation behavior. The cells are discretized as shell elements in the model itself. The temperature is calculated on an element level basis. For the equivalent circuit models, the heat generation is applied on a cell basis. For the distributed model, that is also element level. But basically, it's just a thermal model with heat generated from an electrical equation that is based on test data.
Okay. How do the battery pack temperature predictions with liquid cooling compare to full 3D simulations?
I think we have a fairly accurate solution. Basically, you need to input the boundary conditions on the external part of the cells. So if you don't have a good correlation or something like that, we do have some correlations in TAITherm. If you don't have a good correlation or a good estimate, you can couple directly with CFD and still save time and set up process for doing transient scenarios. So there's a lot of flexibility in how you can achieve that kind of solution with reasonable accuracy.
Okay. What is a node in TAITherm model?
It is just a dimensionless part that has a temperature and sometimes a heat rate in and out of it. So if you're familiar with finite element analysis, it would be like the corner of an element.
Okay. Is there a way to simulate voltage ripple in the charging phase?
Possibly. I mean, the electrical equation is transient for the NREL model. It does predict overshoot. It has a time constant, so when you apply a high current rate and then shut it off, you do see that the voltage overshoots the nominal value and continues going up before it drops back. So if you had a small enough time step, I'm sure you could see stuff like that. But if you're talking about actual electrical design where you might be using ripple as like a design constraint, I'm not sure if it's really built for that. But if you're just looking at we're focusing on the thermal aspect. So yes, it can predict things like ripple if you make a model that's detailed enough to do that, but I wouldn't say it's what our software is designed for.
Okay. Have you tried any abuse conditions on the battery, like nail penetration, crush, etc.?
We've done some thermal runaway simulation where those might initiate the event, but we don't have a mechanical solver. And basically, you would just do something like taking the results of a mechanical simulation or a test and imposing an equivalent electrical resistance in a distributed model to represent ohmic heating and discharge inside that cell, self-discharge. So there are ways to model what happens at that time when you have a penetration event, but you do need to derive some parameters from what that event would create, like electrical resistances between electrodes and things like that.
Okay. Can you present a comparison of the simulation with real-world data on a specific scenario as a proof for the simulation accuracy?
Yeah, we do have some SAE papers that have been published using our software. People are doing validations all the time and publishing new papers, mostly in SAE. So we do have some of those available, and in other presentations we have some validation as well.
All right, and one more. Can TAITherm optimize based on cell experimental data?
Yeah, I'm not sure exactly what kind of optimization you're talking about. We do have ways to derive the cell parameters using optimizers based on test data. And you could run different profiles and things like that, and interface with different softwares. TAITherm also has an optimizer built into it. So when we interface with TAITherm with TAITherm, you can use the built-in optimizer to derive parameters or modify your geometry or boundary conditions to achieve optimal accuracy.
Okay. Well, that will complete today's webinar. We appreciate you attending, and thank you, Zach, for your presentation. You'll receive a follow-up email this afternoon containing links to the download and the presentation slides. Thank you.